Hello, today we're continuing in our series on electromagnetic radiation, looking at absorption of electromagnetic waves. We've already covered in this series what is light, the Poynting vector, the Fresnel equations, polarization, the effect of electromagnetic waves on metal and waveguides, and I've added this further video just to consider what happens when electromagnetic waves are absorbed as opposed to being reflected or transmitted through the material. Let's just remind ourselves that the electromagnetic radiation covers a very wide spectrum, from gamma rays to X-rays to ultraviolet to ordinary light, visible light, to infrared, to microwaves, to radio waves. All of this radiation travels at the speed of light c, but the thing that distinguishes it is its frequency or its wavelength. This is the direction of increasing frequency, this is the direction of increasing wavelength, and of course the speed, which is constant, is equal to the frequency times the wavelength. So as the frequency increases, the wavelength decreases. So here you've got radiation of varying levels of frequency or respective wavelength. We also know from quantum mechanics, which we're not going to dwell on because we'll be doing that in a new series, that the energy of a photon in electromagnetic radiation is given by Planck's constant times the frequency. So the higher the frequency, the higher the energy of the photons. So as you go up this way, as frequency increases, as you go up in this direction in the spectrum, that is why the radiation becomes increasingly more energetic or contains more energy, because each photon contains more energy. So what we're going to do in this video is to start with radio waves and then progress up the electromagnetic spectrum to see how each of these categories will interact with matter when it hits it. We'll start with radio waves. We've actually essentially already done this in a previous video. Here is a radio wave, so it will be fairly low frequency, fairly long wavelength, and it comes up to a metal. That metal will have surface electrons. The electromagnetic wave, remember, is an oscillating electric field. When you get an oscillating electric field encountering an electron, that will cause the electron to accelerate in the electric field, and because the electric field is constantly changing, the electron will simply accelerate up and down in the metal. And that essentially absorbs the energy of that wave, but as we showed in the video on the effect of electromagnetic waves on metals, it also generates a reflected wave which comes back out of the metal. But essentially what is happening here is that the energy of the wave is absorbed by the oscillating electron, which then produces a new wave. But for the purposes of this video, that's what's happening to the energy of that wave. That's how it is initially absorbed. Now let's consider microwaves, and we'll think about a microwave oven. Microwaves are generated in a microwave oven in a device called a magnetron. They are then sent along a waveguide, which we discussed in a previous video. We showed how the energy of waves can be constrained to travel along a waveguide. And they then go into a microwave oven where they bounce around inside. And in so doing, they cook your food. How do they do that? They do that because they are engaged in causing molecular rotation. And that molecular rotation will generate friction, and that generates heat. So you've now got molecular oscillation. A typical frequency of the microwaves for this purpose is approximately 2.5 gigahertz. And if you remember that the speed of light is equal to the wavelength times the frequency, that means that the wavelength will equal the speed of light divided by the frequency, which is 3 times 10 to the 8th meters per second divided by 2.5 times 10 to the 9 hertz, and that comes to 1.2 times 10 to the minus 1 meters, or if you like, 12 centimeters. So the microwaves have a wavelength of about 12 centimeters. And what they do is since these are metal sides to the oven, they will reflect off of the sides of the oven and form standing waves. So let's draw the oven. Here's the oven. Here is the radiation, which is bouncing off the walls and forming standing waves. This distance is one wavelength, so that will be 12 centimeters, which means that the distance between the nodes, the point at which there will be no microwave energy at all, will be 6 centimeters. So the nodes are lambda over 2 apart. They're every half wavelength. And if the wavelength is 12 centimeters, then the nodes will be 6 centimeters apart. And what is actually happening? Well, what these microwaves are really tackling is the water contained in your food. Now, water is H2O, and the way it works is that you've got 2 hydrogen atoms and a fairly big oxygen atom. And what happens is that the hydrogen atoms, which each have an electron, lend those electrons to the oxygen, which is, as it were, incomplete by 2 electrons. And so consequently, if the hydrogens lend electrons, they will become a net positively charged. And if neutral oxygen gets additional 2 electrons lent to it, it will become negatively charged. And you've now got essentially what's called a dipole. A dipole is something where you have 2 charges, opposite charges, that are linked together. They're held together by the molecular structure of water, which of course is H2O. Now, what happens when you've got oscillating electric fields? Those electric fields will cause this dipole to keep flipping. The positive side and the negative side will want to align with whichever direction of electric field you happen to be going in at the time. So it will just flip, 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 flip. That will cause molecular oscillation. That molecular oscillation causes friction. That causes heat. And that is what is cooking your food. But you'll notice that there will be places in your microwave, every 6 centimeters actually, where there'll be no cooking at all, because there is no oscillating electric field. So there will be no cooking. And if you just put stuff in a microwave, you would find that some parts of it would be completely uncooked. That is why a microwave has a rotating table, so that the food always passes through some of the maximum oscillations so that it gets cooked consistently and completely. And now we move up the electromagnetic spectrum to infrared and light and ultraviolet. And here we're finding that the photons of the incident electromagnetic radiation are interacting with the electrons in an atom and exciting those electrons to higher energy levels. So if we take an atom, there's the nucleus, here is an electron that is in theory orbiting the nucleus. In comes our electromagnetic radiation, which might be infrared, it might be light, it might be ultraviolet. And what it will do is it will transfer, the photon has an energy, the energy is E equals hf, where h is Planck's constant, f is the frequency of the radiation, so the higher the frequency, the greater the energy. And what that energy does is that the energy of the photon is given wholly to the electron, and that kicks it up to a higher energy level. So the energy of the electromagnetic wave is absorbed by exciting the electron into a higher energy state. Now, we know from the videos I've done on atomic physics that very shortly after that, the electron will fall back down to the lower ground state, and in doing so it will emit a photon. In other words, it will give off energy in the form of a photon, which you can detect as part of the spectrum of that element. You'll recall that we showed that for hydrogen there are quantized levels of energy. Energy level n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and so on. And that if you have an electron in the lowest energy level, then in order to promote it to one of these other energy levels, the photon that comes in must have precisely the right amount of energy to promote the electron to another energy level. And then, as I've said, it will then fall back down again and give off a photon that equates to that energy level using this formula here, E equals hf. Whatever the energy difference is between the two levels, that will determine the frequency of the photon and hence the frequency of the light. And that is why the photons that emerge when an electron falls from this level to this level all have the same frequency, because they all have the same energy difference, and that will be reflected in a line on a visible spectrum. But not all of these gaps are represented by visible light. For example, to generate an electron, or to get an electron elevated from the n equals 1 level in hydrogen, even up to n equals 2, let alone anything further, requires ultraviolet light. Because only ultraviolet light has a frequency that will give enough energy to get over that gap. Whereas at higher levels, you can promote an electron from this level to this level using infrared radiation. And in the middle, visible light will do the trick. So it rather depends on how close the levels are together, in other words, how big the gap, the energy gap is, call this delta E. However big the gap is between the energy levels determines how much energy the incident photon needs to have. The bigger the gap, the bigger the energy you need, which means the bigger the frequency you need. So if you need to jump over a big energy gap, you need a high frequency, probably in the ultraviolet. If you need a small gap, you need a small frequency, probably in the infrared, with light sitting somewhere in the middle. Now that was electron excitation. Ultraviolet light can contribute to electron excitation, but it can also do something else, and that's called ionization, or the photoelectric effect. Here is the atom, that's the nucleus. Here is the orbiting electron. Here is the incoming ultraviolet photon, and if it has sufficient energy, it can give all its energy to the electron, not to promote it to a higher energy level, but instead to kick the electron out of the atom altogether. It's no longer in a higher energy level, it has completely left the atom. That's called ionization, because now the atom is one electron short, and it is therefore overall slightly positively charged. But the energy for this photoelectric effect must be greater than what's called the work function, or the binding energy of the electron in the atom. The way you can think about this is that the atom is essentially a potential well. This is energy, and the electron is bound to the atom. The reason is, of course, that the nucleus of the atom is positively charged, the electron is negatively charged, so there's an attractive force between the two, which means the nucleus is holding the electron captive. And that, if you like, is like saying it's inside a well. And in comes a photon and transfers its energy to the electron. Now, sometimes all that electron can do is to jump up to a higher energy state and then fall back down again. But we're now talking about the circumstance where that energy is so great that the electron can jump right out of the potential well, can jump out of the holding position, get away from the atom and become a free electron. That's called ionization, and for that you usually need ultraviolet light. We now move up the electromagnetic spectrum to X-rays. And how are X-rays absorbed? Well, they can be absorbed or partially absorbed, more accurately, by a process known as Compton scattering. What happens here is that the photon of the X-rays, which has a frequency f, hits an electron and causes the electron to scatter. But also you get another photon with a lower frequency, f prime. So f is greater than f prime. And that's called Compton scattering. So the X-ray comes in, it gives some energy to the electron, and in losing energy, since remember energy equals hf, as we've said before, if it loses energy, then the frequency must go down as well. If energy is lost, frequency is lost. So incoming frequency, incoming energy gives some energy to the electron. The remaining energy is in a lower energy photon, which means a lower frequency photon. I will derive the Compton scattering formula at the end of this video if anybody is interested in it. If not, you can stop before you get to that point. And finally, we move up the electromagnetic spectrum to gamma rays. And when you've got gamma rays, as we showed in an earlier video, they don't get stopped by very much. They will penetrate many things. In some cases, they will also have the effect of Compton scattering. In some cases, they may even have the effect of the photoelectric effect. But what gamma rays are much more likely to do is to engage in pair production. This is where a gamma ray it doesn't hit anything, it simply comes to a point where it has the energy to create an electron and a positron. That is called pair production. A photon gives up its energy to create two new particles that were never there in the first place. Now, typically what will happen is that positron, which is the positively charged electron, or if you like, the antimatter electron, that will not survive for more than a fraction of a second because it will collide with another electron. Those two will annihilate and they will create another photon. This electron, of course, will survive because it won't, unless it happens to hit a positron, which is unlikely, that will survive. But the key point is that the gamma ray is essentially absorbed by giving its energy to an electron and a positron. Some viewers may wish to switch off now because I have finished covering the absorption of electromagnetic radiation as it passes through matter. I'm now going to do what I said I would do, which is to derive the Compton scattering formula. So if you have no interest in that, you may want to stop. But otherwise, what we said with Compton scattering is that typically an X-ray hits an electron, it gives the electron energy, but it also produces a lower energy photon. And what we can say is that the wavelength of the incident X-ray is lambda. We can say that this is the electron which has been given some energy, moving in this direction, and we can say that the resulting photon will have a wavelength lambda prime, where lambda prime is greater than lambda. In the example I used earlier in the video, I put frequencies here. Of course, frequency and wavelength are simply related by the speed of light. C equals F times lambda. So since we said that the frequency decreases after the Compton scattering, obviously the wavelength will increase. This angle here, that is the angle, sorry, wrong one. The angle here is theta. That is the angle between, as it were, the direction of the incident photon and the direction of the emerging photon. And the formula that we're hoping to derive is that lambda prime minus lambda is equal to h, Planck's constant, divided by the mass of an electron times the speed of light, all into 1 minus the cosine of theta. That's the end point that we are aiming to get to. And incidentally, this term here, h over mec, h divided by the mass of the electron times the speed of light, is called the Compton wavelength. And of course, since it is all constants, you can actually calculate it. It turns out to be 2.43 times 10 to the minus 12 meters, which is in the kind of X-ray region for wavelengths. Okay, so here's the proof. Here is my incident photon with a wavelength lambda incident. Here is my my electron that is given energy, and here is my, at an angle theta, here is my, lambda, gosh I can't draw lambda final, the final emerging lambda. And what can we say of this incident photon? Well, we need de Broglie's equation, and if you remember, de Broglie's equation tells us that the momentum of a photon is equal to h over lambda. That was the famous de Broglie equation, which essentially was the starting point almost of quantum mechanics. Momentum of a photon is Planck's constant divided by the wavelength. So the momentum of this incident photon is going to be Planck's constant divided by the wavelength, which is lambda I. Similarly, the momentum of the emerging photon is going to be Planck's constant divided by the wavelength of the emerging photon. And what about the momentum of the electron, which we will call PE? Well, the series of 5 videos that I did on special relativity, and in particular the 5th video, shows that momentum is equal to energy divided by the speed of light c, and I'll write that down here. The total special relativity energy is given by p squared c squared plus the mass of the electron squared c to the 4th, all in under a square root. That is the energy, p squared c squared plus the mass of the electron squared times c to the 4th, all divided by c. That is the momentum of the electron. It's the energy divided by the speed of light, and the energy in special relativity terms is given by that formula. So we've identified the momentum of the incident photon, the emerging photon, and the emerging electron. We can also say something about the energy of this system. First of all, what is the energy of the incident photon? Well, the energy of the incident photon will be h nu I, where nu is the frequency of the incident photon. What is the energy of the electron, which we're going to assume is at rest before it's hit? Well, that will just be the rest mass, or the rest mass energy of the electron, which is me, that's the mass of the electron, times c squared. That is Einstein's famous formula, E equals mc squared. So the total energy, as it were, coming in is the energy of the photon, which is h nu I, plus the energy of the stationary electron, which is mc squared. And since energy has to be conserved, that must be the energy of the resultant. Well, the energy of the resultant photon will be h nu f, where nu f is the frequency of the emerging photon, plus the energy of the emerging electron, which of course is this here. So that's going to be the square root of p squared c squared plus me squared c to the 4th. Now let's consider momentum, which is of course a vector quantity. So we've got 3 vector quantities, this one, and this one, because the initial electron was of course stationary, so there's no vector momentum for that. And we can draw the momentum vectors in the form of a triangle. The incident momentum goes like this. The electron's momentum looks like this. and the emerging photons at momentum looks like this. Well, let's just label them first. This is the incident photons momentum. This is the emerging electrons momentum. And this is the emerging photons momentum. And of course, if we extend these two here, this angle here is theta. Now we can employ the cosine rule. The cosine rule simply says that the square of this length is equal to the square of this length plus the square of this length minus 2 times this times this times the cosine of that angle. It's just a standard cosine rule of trigonometry. So I'll write it out. PE squared equals PI squared plus PF squared minus 2 times PI times PF times the cosine of the angle theta. Because of course, if this is theta, this is also theta. We can multiply both sides of this equation by c squared, and so we get PE squared times c squared equals PI squared times c squared plus PF squared times c squared minus 2PI PF c squared cosine theta. Now a reminder of an identity that energy is equal to P times c, the momentum times the speed of light, but it also equals h times f, or in our terms h times nu, h times the frequency. Consequently, wherever we have a p squared c squared term, we can replace that by an h nu all squared term. Incidentally, obviously that only applies when you're talking about photons. It won't apply for the electron, but it does apply for the photons. Consequently, we're now going to get that that term stays the same, because that's the electron term, the momentum of the electron squared times c squared equals, well, pi squared c squared is now going to be h nu I all squared. Pf squared times c squared is going to be h nu f all squared. And then look what you've got here. You've got a PIC times a PFC, because this is a c squared, so we can assign one to each. So PIC is going to be h nu I, and PFC is going to be h nu f. So this just becomes minus 2 times, I'll do it again, Pi times one of the c's is h nu I. Pf times the other c is h nu f times cosine of theta. Now let me just remind you of the conservation of energy that we derived, that the energy of the incoming photon plus the rest mass energy of the electron is equal to the energy of the emerging photon plus the energy of the emerging electron, and energy is conserved, so those two terms are the same. We can rearrange that by bringing h nu f over to this side, so we simply get h nu I plus mec squared minus h nu f equals the square root of p squared c squared plus me squared c to the fourth. And now we take a deep breath, because I am going to square both sides of this equation. This side, of course, will simply lose the square root when we square it. This side is going to generate 9 terms. So, deep breath, and we'll write down what those terms become. You're going to get an h nu I all squared from this term. You're going to get, from these two multiplied together, you're going to get a minus h squared nu I nu f. And from this term and this term, you're going to get a plus h nu I times mec squared. Now we're going to deal with this term and multiply it by the others. So we're going to get When it multiplies by itself, you're going to get an h nu f all squared term, because minus h nu f squared is plus h nu f all squared. You're going to get a minus h squared nu I nu f when you multiply this term by this term, and you're going to get a minus h nu f times mec squared when you multiply this term by this term. So far we've got 6. Now we're going to deal with this term. Multiplied by itself, you're going to get a plus mec squared. Then when you multiply this by h nu 1, you're going to get h nu 1 mec squared. And finally, when you multiply that by that, you're going to get a minus h nu f mec squared. So there are my 9 terms, and that's going to equal this squared, which just simply means you lose the square root, p squared c squared plus me squared c to the 4th. This mec squared, incidentally, should have brackets around it. Sorry, that's rubbish. Let me try that again. It was this term here, which is squared, that gave rise to that term, and that would be mec squared all squared. That's the correct term that should have been there. Now, I can simplify the equation, which has got 9 terms on one side and this on the other, by noting that mec squared all squared is the same as me squared c to the 4th. So, since they are on either side of the equation, they can both go. Then I can remind you that we derived a formula for p squared c squared, and that, which I'm showing you now, but I'll just write it out again for you, was h nu I all squared plus h nu f all squared minus 2 h nu I h nu f cosine theta. That was, you remember, the consequence of the cosine rule. So these now 8 terms, because I've lost one, these 8 terms equals p squared c squared, but p squared c squared equals these terms here. And that means we can now lose a bit more, because you'll notice we've got an h nu I all squared here and an h nu I all squared here, so they go. We've got an h nu f all squared here and an h nu f all squared here, so they go. And now we just need to tidy up what's left. Well, look, we've got 2 lots of these terms here, the h squared nu I nu f. So we've got minus 2h squared nu I nu f. And then we've got this term, or these 2 terms here, can be written as plus h mec squared into nu I minus nu f. That's those 2 terms there. But you've got the same 2 terms there and there. So this is effectively twice. That takes account of this one, this one, this one, sorry, this one, this one, this one, and this one. And that deals with everything on the left-hand side, so we've now only got what will be on the right-hand side, which is all we've got left of this term is minus 2h nu I, h nu f cosine theta. And the first thing you can do is to divide through by 2 throughout, so all the 2's go. Then I'm going to take this term here and write it like this. That is mec squared into, take the h inside in each case, h nu I minus h nu f. That is that term, just rewritten, is equal to, and I'm now going to take this term over onto the other side. This is an h squared nu I nu f. So I'm going to, and I've got an h squared, because those 2 h's become h squared nu I nu f. So when I take this over to the other side, I'm going to get a plus term. So I'm going to get an h squared nu I nu f. And that will be into 1, which is coming from here. It becomes plus 1 because I'm bringing it over to the other side. Minus this term here, which is minus cosine theta. And you're just beginning to see the beginnings of the derivation of the formula. We're almost there. I am now going to divide all those terms by MEC squared h nu I h nu f, which will be a lot easier than you think, because when I divide this term by that term, the only thing that is left is a 1 over h nu f. That's from that term. When I divide MEC squared h nu f by this term, the only thing that's left is a minus 1 over h nu I. When I divide this term by this term, remember this is an h squared here, so I've got an h squared, nu I, nu f cancels that. I get a 1 over MEC squared, all into 1 minus cosine theta. I don't have to divide that by this term because this is a product, so I only need to divide one part of the product. Now I remind myself that lambda nu is equal to c, and that means that nu is equal to c over lambda. So I replace nu by c over lambda in each case, and that will give me that lambda f over hc minus lambda I over hc is equal to, well, this term won't be affected, so it's just still 1 over MEC squared 1 minus cosine theta. Now I can cancel the c's, so that c goes, and one of those c goes. And now I can multiply both sides by h, so I get that lambda final minus lambda initial is equal to h over MEC into 1 minus cosine theta. And that was the formula for Compton scattering that we were trying to find in the first place. So the higher the frequency, the higher the energy of the photons. So as you go up this way, as frequency increases, as you go up in this direction in the spectrum, that is why the radiation becomes increasingly more energetic, or contains more energy, because each photon contains more energy. So what we're going to do in this video is to start with radio waves and then progress up the electromagnetic spectrum to see how each of these categories will interact with matter when it hits it. We'll start with radio waves. We've actually essentially already done this in a previous video. Here is a radio wave, so it will be fairly low frequency, fairly long wavelength, and it comes up to a metal. That metal will have surface electrons. Hello, today we're continuing in our series on electromagnetic radiation, looking at absorption of electromagnetic waves. We've already covered in this series what is light, the Poynting vector, the Fresnel equations, polarization, the effect of electromagnetic waves on metal, and waveguides, and I've added this further video just to consider what happens when electromagnetic waves are absorbed as opposed to being reflected or transmitted through the material. Let's just remind ourselves that the electromagnetic radiation covers a very wide spectrum, from gamma rays to X-rays to ultraviolet to ordinary light, visible light, to infrared, to microwaves, to radio waves. All of this radiation travels at the speed of light c, but the thing that distinguishes it is its frequency or its wavelength. This is the direction of increasing frequency, this is the direction of increasing wavelength, and of course the speed, which is constant, is equal to the frequency times the wavelength. So as the frequency increases, the wavelength decreases. So here you've got radiation of varying levels of frequency or respective wavelength. We also know from quantum mechanics, which we're not going to dwell on because we'll be doing that in a new series that the energy of a photon in electromagnetic radiation is given by Planck's constant times the frequency. But for the purposes of this video, that's what's happening to the energy of that wave. That's how it is initially absorbed. Now let's consider microwaves, and we'll think about a microwave oven. Microwaves are generated in a microwave oven in a device called a magnetron. They are then sent along a waveguide, which we discussed in a previous video. We showed how the energy of waves can be constrained to travel along a waveguide. And they then go into a microwave oven where they bounce around inside. And in so doing, they cook your food. How do they do that? They do that because they are engaged in causing molecular. The electromagnetic wave, remember, is an oscillating electric field. When you get an oscillating electric field encountering an electron, that will cause the electron to accelerate in the electric field, and because the electric field is constantly changing, the electron will simply accelerate up and down in the metal. And that essentially absorbs the energy of that wave, but as we showed in the video on the effect of electromagnetic waves on metals, it also generates a reflected wave which comes back out of the metal. But essentially what is happening here is that the energy of the wave is absorbed by the oscillating electron, which then produces a new wave.